All right, in this lecture, we're going to talk about pandas. Pandas, like NumPy, which we've already talked about, is an external library that we must import into Python. And it is really the primary external library that people use for transforming data. We'll talk about some of the ways we can transform data and other things we can do with pandas in this lecture. Just like it's idiomatic to import NumPy as MP, similarly, you'll see this all over the documentation, everywhere, Stack Overflow, the web, that it's often, or it is the case where it's idiomatic to import pandas as PD. So once we've done that, we can read in some data. In this case, we have a data file that is a comma-separated value file. This is a common format for storing data. And we read that into pandas with read CSV. And this read CSV command is very powerful and may be in and of itself enough reason to use pandas in some applications, because it has very sophisticated ability to ignore certain headers and footers and parse dates, and just in general parse data from a file in a very efficient and clean way. Once we read that in, it's stored as a so-called data frame object. So DF is an object, a data frame object that is part of pandas. And one of the member functions that is defined on data frame objects is head. By default, head will print out the first 5 values, the first 5 rows of a data frame. So it kind of gives you a preview. Turns out this data set actually has 200 rows, and we'll rarely look at all of them because it's just difficult to visualize on a slide. So you'll see this often, this head. Head does accept an argument. The default is to display 5 rows, but you could give it an argument if you wanted to display 10 or 15 or 20 more of the data set. So in this data set, we have X and Y. These are geographic spatial locations. Facies threshold, there's just either an integer 1 or 2. It corresponds to either sandstone or some type of mudstone. Porosity values, permeability values, and acoustic impedance. So this is the data set that we're reading in. Another member function of the data frame object is describe. So we can call describe on a data frame, and it will automatically generate some useful summary statistics. For example, the count is simply the number of values for each of these labels. The mean is the average value, the standard deviation, min, max, and different quartiles. So this is useful to get a quick look of a summary of what's in the data frame. We can take parts of the data frame. We're familiar with slicing type operations in NumPy, and in some cases these indexing or selecting operations correspond to those, as we'll see. It's often the case that we want just one column. If we want to do that, we can refer to it by its label. Again, so in this case, I'm just pulling off the porosity column and printing out the first 5 rows. You can pull out multiple columns from a data frame by passing it a list. So in this case, the porosity and permeability. You'll notice over here on the side, there's this monotonically increasing set of index. These are just the labels of the rows. In pandas, we call those index. A lot of times they're just monotonically increasing integers like this. However, in time series data, it's often the timestamp right over here as the index. We can do different types of label-based selection. So we can use the member function loc in this way to select not only the column, but the row number as well. So in this case, we're going to take the 1 and 2 index, so in this case, the index serves as the label. So we're going to take the 1 and 2 indexed row and take the porosity and permeability columns. Loc also supports NumPy style slicing notation to select sequences of labels. So again, we'll take from 1 to the indices, and also from porosity to acoustic impedance in the data frame. So if we go back and look at the original data frame, you'll see that in the order that they were originally, it was porosity, permeability, and acoustic impedance. So we can use this NumPy style slicing to get everything in between. We can also get index-based selection. So we have iloc for that. In this case, we're going to refer not only to the index, the row by its index, but also the column by its index. So again, if you go back and you were to look at the original data frame, you'd see porosity and permeability are the 3 and 4 indexed, from 0 columns of the data frame. And so that's just another way to get information from the data frame. Often the reason we use Pandas is because we want to refer to the data from its label. So this is less useful, except perhaps if you're maybe looping over and you want to loop over the integer columns instead of the labels. But often, we prefer to use Pandas simply because we can refer to the columns via their label, which makes our code more readable, right? If we want to do an operation with porosity, it's nice that we can refer to it by its label instead of the 3 column, right? iloc supports the Python list style slicing. We can get data, the underlying data, as a NumPy array. So for example, if we wanted to sort of ignore the index and just have it return an ND array that is a NumPy array, we can say the data frame porosity, and then we use the attribute values. So that will ignore the index and just return the underlying data in the data frame. Of course, this is a NumPy ND array, and we can then use any kind of standard NumPy operation on it. We're going to look at some other types of transformations of a data frame. For example, the original columns, as they were in the file, the column labels were kind of long. Facies threshold, 0.3, permeability, acoustic impedance. If we wanted to create shorter labels so that we could refer to them in a more compact way, we can use the data frame rename command, passing it the argument columns as a dictionary. So the syntax here is the original column name and the new column name that you want. We also use the in-place command or argument here, which in this case will transform the data frame in place, meaning it doesn't return a new data frame. It actually changes the data frame in memory in place without returning a different data frame. We can add a new column to a data frame. You'll notice that data frames often use syntaxes very similar to Python dictionaries. So with the Python dictionary, if we wanted to get the values or set a new value keyword pair into the dictionary, we would use this type of syntax where this is the keyword that would go into the dictionary, and then what it's equal to would be the value. So very similar here in Pandas. We want to set a new column with the label 0, and in this case, the column is just going to be a NumPy array of zeros. That is the original length of the data frame, 200 in this case. And then we're just printing out the first 5 rows. So you see over here, we've added a new column to the data frame. We can also then remove columns. In this case, we're going to just remove the column that we just placed there. We're going to do that with the drop command. We give it a label. In this case, if we want to drop a column, we do have to specify the axis because the default is 0. And that would be a row. In this case, we want to drop the column, so we'll say axis equal to 1. And again, we want to do it in place, meaning the zeros column will be permanently removed from the data frame in memory. And again, we're just printing out the first 5 rows with the head command. We can also remove rows with the drop command. In this case, the axis is defaulted to 0, which implies a row. So in this case, if we wanted to drop the 1 index row, we could do it like this, and then we're printing out the first 5 rows. And if you notice, the index here, the 1 row is missing, right? So we've removed it. Also notice in Pandas, you can stack these member function commands, right? So In this case, we're dropping and then immediately printing out the data frame of the first 5 rows. We can sort data frames. So in this case, we start to recognize that a lot of these operations are similar to things that you would do in Excel. So we have this kind of 2-dimensional tabular style data, and we want to sort it. And in this case, we're going to sort it based on porosity in descending order. And again, do it in place, which will change the order of the data frame in memory. In this case, I'm printing off the first 13 rows, and what you'll see is that the original indices are all jumbled up now. We can reset those indices with the reset index member function, again, in this case, in memory, in place. And so you'll see where this just resets the indices to be monotonically increasing. And again, we are printing off the first 13. In the field of data science, feature engineering is a term that's used to transform existing features into new features that might be more useful for analysis. And so in this case, we're going to create a couple of new columns in the data frame. One of them is going to be just a conversion from the fractional porosity as it was originally to a percentage. So in this case, we're going to have a new column that's called percent porosity. And that's just the original column porosity times 100, of course. We're also going to have another column called perm-pore ratio, which is the permeability column of the data frame divided by the porosity column of the data frame. Notice that we can do these mathematical operations directly on the data frame columns. We don't have to extract the values of the NumPy array. These type of things will work directly. So again, printing off the first 5 rows of the result, you'll see that in fact the porosity has been converted to a percent, and this is the ratio between the 2 columns of permeability and porosity. You can do other things, just more feature engineering here, and using some NumPy commands. So we're going to create another column that we'll call porosity type. This is either going to be valued as a string high or low. And we're going to use the NumPy where command to determine that. So basically, if you remember the syntax for NumPy where, the first one is a Boolean array. The second one is the value if true, and the third argument is the value if false. So in this case, what we're saying is if the value of porosity in the data frame is greater than 0.12, we're going to give it the label high. Otherwise, we'll give it the label low. And then I'm just using some NumPy style indexing, fancy indexing, to get a few of the values that are high. In this case, it's just the first 3 values of the data frame we're printing out. You can see all of those are high. And then I'm also just wanted to grab some of the low ones. In this case, you see you have to go to index 165 before any of the low ones appear. But just you can see that these are, via their index, these are a different location in the data frame. So a similar operation, but instead of just assigning a high or low value, what we'll do here is say where the porosity is greater than 0.12, we're just going to pass the permeability through. And if it's less than that, we're going to just set it to a very small number, 0.001. We'll call this permeability cutoff and add a new column to the data frame. And again, what I'm doing here is just showing you, in some case, the first 3 where the porosity value was high, the permeability is simply passed through. And the first 3 where the porosity value was low, we cut off the permeability to a very small number. Again, this is just an example. It's very often in data that we have missing or invalid data. And so Pandas has quite a few built-in features for dealing with missing data. In this case, the first thing, our original data frame did not have any missing data. So let's add a missing data in there. So we'll use the @ command, which is similar to loc in a way, but is only used for accessing a single value, and it's very fast. So in this case, we're going to take the one index of porosity and set it to none, and then if we print off the first 3 rows of the data frame, you'll see that there is actually a nan there, not a number, appearing in that location. So we explicitly put it there in a location that we know, but it's often the case that when we have data or we read it in, that it's unknown. The isNull member function will return a Boolean array that identifies rows that are missing. So in this case, I'm going to again use the NumPy style fancy indexing to basically find the rows in the total data frame. Of course, in this case, there's only 1 because we explicitly set it. But here we're printing it out, and in fact, you can see it's the one index row that this is returned, right? So we're using fancy indexing. This df porosity isNull returns a Boolean array, right? Trues or falses. True where we have missing data. And then we're just printing it out with this fancy indexing command. We can drop missing data from a data frame with the built-in drop NA command. So in this case, we have that data frame that had the missing data in one index, and we can just simply call drop NA. Again, we'll use in place equal to true, which will cause the data frame to be changed in place, and it doesn't. And this function will not return a new data frame. We can then again print out the first 3 rows. If you recall, it was the one index where we had a porosity value that was missing, and now you see that it has been dropped from the data frame. We could re-index this. We've seen how to do this. Up to now, we've been dealing with data that was read in from a file. We can also create new data frames from scratch. So the first thing we'll do is use NumPy to create a list of, or an array of random porosity values that go from 0 to 0.2. And then we'll use the Kozeny-Karman relationship to convert those porosity values into permeability. So we have this nonlinear relationship between porosity, and we'll use that to give us permeability values. So as of right now, porosity and permeability are just NumPy arrays. If we wanted to stick them into a data frame or create a data frame from scratch from them, first thing we can do is create a dictionary. This is just a regular Python dictionary where the keywords are going to be your desired labels in your data frame, and the values are the data, in this case, the NumPy arrays. Then we'll pass this dictionary as an argument to PD data frame to create the data frame. So in this case, we have a data frame df new that we create on the first line, and then we just do some sorting because later we're going to plot this, and so we want them to be monotonically increasing. So and because they were generated randomly, there's no guarantee that that would be the case. So we're going to sort them based on porosity in place, and then go ahead and re-index it with this ignore index equal to true right now, and then print out the first 5 rows. We can also merge data frames. So in this case, we're going to take 2 selections from our original data frame with iLoc, and then we're going to call those df1 and df2. Again, it's just the first 3 rows of the data frame, and from index 2 on to the end for the columns. For df1 and df2 is similar, except now we're just taking the rows 10 to 13. So now we have 2 data frames, and we can then concatenate them with this command. So Pandas PD concat the data frames in a list and the axis which we want to concatenate it on, right? And this is a axis equal to 0 refers to the rows. So here I left the indices in there so that you can see 0, 2, 3. There's our first 3, and now 11, 12, 13. So you can see that what the data frame displayed in the bottom is just simply the 2 data frames above it stacked together on top of one another, or concatenated along the rows. Another nice feature of Pandas is the built-in plotting. So if we just call plot on a data frame, it will plot all of the columns against their indice, right? And so in this case, this is what we have, right? If you recall, our original porosity values were randomly generated, and then we had a nonlinear relationship between them for permeability. However, it's not really useful here to plot them against their indices. That's just a monotonically increasing set of numbers. There's a couple of things we can do to get the plot to be more useful. One of them would be to set the index to porosity. So if we set the index to porosity of the data frame and then call plot on it, now we have porosity on the x-axis and permeability is the y-axis displayed in the label here, and you have this relationship. We can also just do this more explicitly from the original data frame. So if we take the original data frame, in this case, I'm calling a scatter plot, so plot.scatter, and then I'm explicitly giving it x and y axis labels. And so in this case, a scatter plot, because the default would be a line, the dots would be connected. In this case, we're just plotting the individual data points as dots, circles. And we're going to set the x-axis to porosity and the y-axis to permeability to get this nonlinear relationship. Finally, after we've done some transformations on a data frame, it might be useful to write that to a file so that we could then import it into Excel or send it to someone else for further manipulation. And the data frames have this built-in toCSV command, which can, then you just give it a file name, in this case, 200 wells out. And we're going to remove the index from the data frame because, again, those kind of monotonically increasing integers aren't that useful. If then, in this case, we wrote to a file that's on my hard disk here, and I can use the Unix head command to actually look at the first 5 files. So, we don't get the nice display that we get in a Pandas data frame, but it is essentially the same thing. The first row here are the labels, and then all of the values below it in comma separated value form. There are many other things you can do with Pandas. The documentation is really great. There's lots of examples online. For example, you could have some complicated function that you could then map across or apply to every value, every row for a label in a data frame, which gives you very much Excel-like features, but far more powerful because you have the full power of Python and NumPy to do the manipulations.